Okay, so for our last example, we're going to do something a little different here, and we're actually going to look at this formula for the nth antiderivative of sine. In other words, sine raised to the n power. We're going to take the antiderivative of that. That's probably a better way to say that. So, and we see that it's this formula here, and what we want to do is prove that formula is actually that. And then we want to use it to figure out what the antiderivative of sine squared x is, and what the antiderivative of sine raised to the fourth x is. Okay. So to start this, notice that we are going to be using integration by parts here. So this integral here is going to be integral of all of this is going to be u times dv, okay? And what we're going to have here may very well end up being, well, it actually is going to be uv times integral of v du, okay? So it's going to look something like that. I notice here that for this first term, I have a sine raised to the n minus 1, and I have cosine here, okay? So what that's telling me is that either sine raised to the n minus 1 of x is going to either be u or v here, okay? Since I have to choose between u and dv, that kind of gives me a hint here to let u equal sine raised to the n minus 1 of x, which is the same as saying sine of x raised to the n minus 1. And if we do that, then it means that dv is just going to be sine of x dx. And again, if I multiply sine of x by sine of x raised to the n minus 1, the exponents add here, because it's like sine of x raised to the 1. Those exponents add to go back to just sine raised to the n. So that works out. So from here, what we'll do is just set up our integration by parts and kind of see where it takes us. Okay. So here we'll say integral of u dv, which you know is the same as saying integral of sine raised to the n of x here. It's just going to be uv minus integral of v du. And our u here, again, is just going to be sine of x raised to the n minus 1. And I'm going to write it like that until we don't have to use it anymore. Our v, of course, we haven't figured that out yet. But if dv is sine x dx, then it means that the antiderivative of sine is going to be minus cosine. Okay, so our v here is going to be a minus, I'll do a minus cosine of x. And this will be minus integral of our v again, which is minus cosine of x. And now du, I'm going to write that in a different color here. So let's see, I'll do it in black. So if u is this, then du is going to be n minus 1, using the chain rule here, n minus 1 times sine of x raised to the n minus 2. And then, of course, if we take the derivative of the inside function sine x, that is going to be cosine of x. And then dx. So all that's got to fit in here. So I'm going to have to make a little room to make that work here. Or what I'll just do, I'll just cheat And we'll just do this. Say all of that goes here. Okay. And then I'll just write it all out in the next step. All right. So therefore, it's integral of u dv. What we end up having here again is this minus sine of x raised to the n minus 1 and this will be that times cosine of x, and then this will be plus cosine of x times, and now we got to write all this stuff in, n minus 1 sine of x raised to the n minus 2 times cosine of x dx. And so if we notice here, we know that cosine and cosine multiply to be cosine squared. So I'm going to go ahead and simplify that. We also see that n minus 1 is a constant. So we're going to pull that n minus 1 on the outside. So here I'm going to rearrange this to where I have cosine squared x here. And we'll get rid of that there. And we'll have n minus 1 like this. And then we'll do the integral. And of course, all this business here would go with the integral. All right. Now, the next thing that we see here is that cosine squared, it's not going to do us much good to leave this as it is. But we do know that cosine squared is 1 minus sine squared. Okay. And in doing it that way, that will force us to have a sine of x raised to the n minus 2 term, like what we need here. So what I'm going to do next here is just going to rewrite this totally, and I'll just go ahead and drop to the next line to do that. So here we'll keep all the rest of this the same. X raised to the n minus 1. Seems like my pen is just getting worse and worse. All right, let's try one more time. X raised to the n minus 1. All right, and then we got n minus 1 here. Integral, and instead of writing cosine squared, we're going to write 1 minus sine squared. And we'll multiply that times sine of x raised to the n minus 2 dx. Okay. All right, so now that we have that in place here, we see that we can take this and distribute it to both terms. And of course, we'll have that sine of x raised to the n minus 2 dx like we want, but we're also going to have another term that's just going to be sine squared times sine x raised to the n minus 2, which is just going to leave us with sine sine of x raised to the n, okay? And we want that as well because remember, that is what this actually is, okay? That's what we started off with, okay? So we don't want to forget that. So here, since we don't want to forget it, I'm going to go ahead and write it in here. This is going to be sine of x raised to the nth power and here, of course, need to rewrite all the rest of this stuff. Cosine of x plus n minus 1. And here we're going to have two separate terms here. So this would be n minus 1 with the sine. Oh, let me not write it like that. All right, so sine of n minus 2 of x. I'm going to write it like this for now. And this is also going to be minus n minus 1. And of course, sine squared times sine of n minus 2 squared is just going to be sine raised to the n. Okay. And so if we look here, we'll see that this term and this term are like terms. So what we could do is add this term to both sides. And if we do that, we're going to have 1 plus n minus 1. And of course, 1 plus n minus 1, that just equals n. So on the left side here, this will just simply be n times sine raised to the n of x dx. That is going to equal everything else that we have here, which is going to be minus sine of x n minus 1 times cosine of x plus n minus 1 sine raised to the n minus 2 of x dx. Okay. And so finally, we see here that in order to get sine raised to the n of x dx, the integral of that by itself, we would have to divide both sides by n here. Okay. And if we divide both sides by n, then of course this goes away. And we would have over here both terms here being divided by n. So I could just come here and just divide this by n and divide that by n, and that would take care of both of those terms. And if we come back up here, we'll see that that's kind of what happens here. The 1 divided by n that's there would be understood 1 divided by n here. And of course, the n minus 1 divided by n, that is what we see here. And everything works out. So now that we have a way of expressing the antiderivative of sine raised to the n of x dx, then of course we could use this formula to be able to figure out what sine squared, the antiderivative of sine squared would be, the antiderivative of sine raised to the 4th. And so instead of trying to write that all out, I already have that worked out. So I'm just going to show you what it looks like. And then we'll go ahead and end this video here. So let me just show you what that looks like when we work it out. So if we use that formula to figure out what sine squared of x dx is going to be when we take the most general antiderivative of it, of course we use that same formula here, and you see that we'll get minus 1/2 sine x cosine x. And then, of course, this is the n minus 1 over n part. And this just ends up being another 1/2. Of course, sine raised to the n minus 2 power, since n is 2, because since that's what n is here, then of course this ends up being just some constant. And of course the antiderivative of a constant is just going to be a linear term there. And so that's how we get the 1/2 x there. And that ends that. And so of course here, this is actually an acceptable answer. But we do realize here that sine x times cosine x here is the same as 1/2 of sine of 2x. So we can write that in a more condensed form here. And so we see that if we replace sine x cosine x with 1/2 of sine of 2x, then we just get negative 1/4 sine of 2x plus 1/2 sine x plus c. Okay. Now, we see that if we use sine raised to the 4th, we have a little bit more work to do because we have to use this formula twice. So here we see that since n is 4, of course, 1 over n sine raised to the n minus 1 cosine of x, and then of course n minus 1 over n times sine of n minus 2. Notice here that all this on the outside works out fine, but here we have the integral of sine squared, and of course what we just found out there, we would just go ahead and substitute that in to keep from having to recreate the wheel. And then of course from there, the rest of this is just us trying to do what we can to simplify this, to make this look as nice as possible. Okay. And of course, I break up this sine of x raised to the 3 and into sine squared times sine. Of course, for the fact of sine x times cosine x is 1/2 sine of 2x. And then here we also realize that sine squared is going to be sine squared of x is going to be 1/2 of 1 minus cosine of 2x. That's one of your trig reduction formulas. And so if we use all that information here, of course, we'll substitute in 1/2 times 1 minus cosine of 2x here. See all that substituted in. And then from there, it's just a bunch of arithmetic to try to get it down to something that looks, relatively simple. So, and of course, we get to this final answer here. All right, so I know this was a long video, but I had a lot of examples, and I wanted to make sure that I showed you a lot of examples because integration by parts is very important. For those of you that will be taking higher math courses, or you will be using this in the future, you're going to see integration by parts a lot. So, and again, that's one of the reasons why I wanted to make a lot of examples so that you don't get thrown off based upon some examples that you see. I had a lot of easy ones, some that were a little bit more tough, a little bit interesting, but I think with this, you will have enough to be able to at least have a foundation in how to do integration by parts. And I really hope this helps in your understanding. Take care.